Hi again, everybody. It's time for another AP Calc lesson. This is the second lesson in Chapter 4. We'll be spending a couple days on this, but this is the nuts and bolts of it, specifically the mean value theorem. And here it is in words and kind of a nice little diagram here. So the function has to be continuous in a closed interval. Remember, a closed interval means that these endpoints here have to be defined, and it has to be differentiable at every point of its interior. So remember, if we had like a corner or a cusp, then that doesn't apply. It has to be a nice differentiable curve in the middle there, in the interior. Anyway, if those two conditions are met, then it says there is at least one point C, somewhere in this interior, at which the derivative at C has to be the same as this, in a sense, average rate of change. Notice this is our slope expression, but basically it's our change in y over change in x from the two endpoints. So an interesting theorem saying that someplace in this interior, that derivative, that slope, is the same as the slope between these two endpoints. So we'll be doing some work with this in this particular lesson. Alright, here's our first little example here. So it says we want to show that this function f of x equals x squared satisfies the hypotheses of the mean value theorem on this given interval, and then find that c value that satisfies the theorem. So we're looking at from 0 to 2, so I'm just going to kind of mark that. There's 0 and here's 2 right in there. So again, let's just think back to the conditions or the criteria here for this to work. One of them is that the endpoints have to be defined. It's a closed interval, which we can tell by this notation, 0 and 2 count. And the other idea was that it's differentiable on the inside. And of course, this is a nice smooth curve, so it is going to be differentiable. So that works. But now we want to see if we can actually find that c value that satisfies that theorem. All right, so let's first of all do this. Let me get to my pen here. First of all, we better find the derivative of this function. And of course, this is a pretty easy one. It's just going to be 2x. So the theorem then says, I'm going to call it 2c because we're really trying to find what that c value is. And remember, what this would essentially say is we're trying to find the f of 2 minus the f of 0, all of that over 2 minus 0. And if we go ahead and look at the theorem, of course the f of 2 would be 4, the f of 0 would be 0, 2 minus 0 is 2, so we end up here 4 over 2, which is just going to be 2. And 2c equals 2, and sure enough that means that c equals 1. So that would be something that you could check on your calculator if you graph y equals x squared, and then if we actually look at this point right here, when x is 1, or c is 1 in this case, so it should have the same slope as the line that connects these two endpoints. So we'll work on this certainly a lot more in class the next couple days, but this is good. Puma, don't do that now. My trusted assistant and nuisance, Puma, helping me out here. Alright, now let's go to the next slide. And here we have a nice chart that you should take some time to write down. One big theme in this lesson is the whole notion of increasing and decreasing functions, and how you can tell that not only by looking at the initial function, but also at the derivative. So here's the f of x, and here's the derivative here, decreasing and increasing. And I think you just kind of common sense here in that a decreasing function, as you move left to right, the y values will get smaller or decrease. So that seems to be intuitively correct, I believe. And the same thing with increasing. As you move left to right, the y values would be getting larger. And so that's pretty common sense, I think. What we'd like to be able to do, though, is tell some things about the original function by looking at the derivative. And here's kind of a key thing. I think, have touched on this a little bit last chapter, but here, this chapter is where we'll really hit this pretty hard. If I look at the derivative, anytime the derivative, when it's less than 0, in other words, when the y values are less than 0, notice that's going to say that the original function is decreasing. And whenever the y values of the derivative are greater than 0, in other words, they're going to be graphed over the x-axis, that is when the original function is going to be increasing. Now, here's my specific example here, x squared minus 6x plus 7. It's a parabola, of course. We can easily tell when it's decreasing and when it's increasing just by looking at the actual function. And we can see that the lowest point here occurs when x is 3. Now, if I take the derivative of this, which we know is going to be, I'll just write it down right here. So y primed would be 2x minus 6. If I graph that, of course, that's going to be a straight line. Look at where that crosses the x-axis when x is 3. So anytime x is less than 3, situation like this, it's graphed underneath the x-axis. That's going to represent a decreasing situation with the original function. Anytime the derivative is graphed above here, when y is greater than 0, that's going to represent an increasing function, or increasing interval on my original function. And of course, remember that when we talk about this increasing or decreasing, we always describe it with the x values. The x values. And always look left to right. I think that's the best way to understand those. So this is a huge part of differential calculus, is looking at the graphs of the original function, the first derivative, and eventually we'll even look at the second derivative and be able to tell a lot of stuff about the function without even having to graph it. This was put in here just for your benefit to help you understand a little bit better, but as we'll see on the next slide, we're going to try to determine this without even graphing it at all. So here's our next example here. And so I have this particular function, x squared minus x minus 12. When it says analytic methods, you'll see that on our assignment quite a bit. Analytic methods simply mean to do it algebraically without the use of any calculator. Now we can still use our calculators to double check, to verify what we've done, but we'd like to be able to do all this without using a calculator. So the first thing we'd like to do is let's pretty much just examine the derivative of this. And so that's not too tough. With our derivative rules, now we know that this is going to be 2x minus 1. Now a key thing that we will often do with derivatives is we're going to set this equal to 0. Because at that particular point will be a very key point in our derivative and also in the original function. So in this case, I'm going to get 2x equals 1 and x equals 1/2. So the idea is, if we picture or imagine the graph of this function, it's going to cross the x-axis at x equals 1/2. And so when x is less than 1/2, something's going to happen. When it's greater than 1/2, something else is going to happen. And that's where my increasing and decreasing is going to occur. Alright, so let's think about that a little bit. Let's just think about the derivative again. Let's just pick a point that is less than 1/2, like 0. So if I put 0 in for the derivative, 2 times 0 is 0, 0 minus 1 is negative 1. So if my derivative is negative 1, if you think back to the last slide that we had, which was that chart, anytime the derivative is less than 1, that means the original function is decreasing. Look back on your notes that you just took on that. And just to verify this, let's pick a number that's clearly bigger than 1/2, like 1. And sure enough, if I put a 1 in the original derivative here, 2 times 1 is 2, 2 minus 1 is 1. So there, my derivative is positive. That means, in that region anyway, that the original function is increasing. So the local extrema that I'm looking for here, I know for sure that that's going to happen at 1/2. And so I can say then that at x equals 1/2 is going to be, well, what kind of extrema? Do you think it's going to be a maximum or a minimum? Well, if the function goes from decreasing to increasing at x equals 1/2 there, then that's going to be some sort of minimum. And it says local minimum. It very well could be. Local, remember, means kind of like the relative one, but it could also be the absolute maximum or minimum as well. So anyway, we were able to tell this from this original function by not even graphing it at all, just by doing these analytic methods. Now, we could go ahead and graph this and just verify that this will be true, but we'll find that it indeed is. All right, here's a couple of corollaries. What corollaries are in math are just kind of extensions to theorems. They could be proven, but we won't take the time to do that here now. And we have sort of talked about these, maybe not stated this directly. But first one is this, that if the derivative of a function is 0, we know that function then must be a constant. That means a single number. And representing that, it would just be a horizontal line. And another one that, if you think about it, makes sense. Functions with the same derivative differ by a constant. So just for an example of what that might mean here, functions with the same derivative, if I had f of x equaled x squared minus 3 and g of x equaled x squared plus 7, clearly they're going to have the same derivative of 2x, but they're not the same function. But that function will only differ by a constant. All right, and lastly then we have this thing called the antiderivative, and that antiderivative is, as you can read here, kind of the backwards or going in reverse. So if you know what the original function is, can you think backwards and try to find what function would produce that as a derivative? So anti-differentiation. And we'll do a little bit of that here. That will especially become true, I would say, next quarter when we study about integral calculus. But just a quick example how this might work. I'm kind of running out of time here a bit, I think. So let's say that the original function they give you is x plus 3. I'll just make it even easier, 2x plus 3, let's say. Well, the antiderivative of that would be some function that gives you this as a derivative. So it would have to be x squared, because the derivative of x squared is 2x, and this would have to be plus 3x, because the derivative of that big F would be this. Now I could also tack on some constant here because we don't know exactly what that is. All right, finish out one little problem here we have. Let me change pen colors. Find the function whose derivative is this. So we're looking in a sense for that antiderivative, and whose graph passes through that point to -3. So we want the original graph to pass through that, and it has to have that as a derivative. Well, let's think about that now. So I'm looking for this big f of x. And remember, if I'm trying to find that antiderivative, I have to have bigger powers. So I think it's going to be x to the third, because the derivative of that is 3x squared. Then it would have to be minus 2x squared. Remember, the derivative of that would be negative 4x. And then plus x, or 1x. And I am going to tack on this plus c here. Later on we'll see that's quite an important thing to do in calculus. So here's my particular function. I know that this point 2, -3 is on that particular function, so what I can do then is just substitute that, because I want to find what this c value is. So I'll put -3 in place of that big F, that's kind of like my y value, and I'll put 2 in place of the x here, and see what we get. I'm trying to solve this for c. So I get negative 3 equals 8. 2 squared is 4, minus 2 is 8, plus 2 plus c. So I'm going to get negative 3 equals 2 plus c. Then I'm going to subtract 2 from each side, so c is going to be negative 5. So that big f of x, now I know exactly what that function is. It is specifically now going to be x cubed minus 2x squared plus x minus 5. That's the original function. Derivative is this, the original function that passes through that point. All right, thanks for listening. We'll be working on this for a couple days in class. Bye now.